everybody, welcome to the next video in this video sequence. Here we're talking about the curl. So remember that in two dimensions, we have some vector field that looks like FG. The two-dimensional curl, the curl of F was the scalar. This was partial G, partial X, minus partial F, partial Y. Partial F, partial Y. And remember, this measured rotation around a point in the XY plane. Now, this is not as easy to extend to 3D, right? So in 3D, our vector field will look in general like F, G, H, and it's not clear, at least from this definition, how we would extend that to 3D. And in fact, it doesn't extend that nicely. Well, I'll point it out. I'll point out the extension. But in general, in 2D, right, there's only two ways for the vector field to rotate around a point, right? We have some point like this. The vector field might rotate in the counterclockwise direction around the point, or the vector field would rotate in the clockwise direction around the point, something like this. So here, the curl, it's a rotation, right? So use the right-hand rule, put your hand down. My fingers are curling in the direction of the arrows. The curl is actually coming out towards me. This is positive. This is positive curl. Oops, I don't want green. This is positive curl. And more than just positive, it's coming out at me. I can actually describe a direction to that. That this is a positive curl, it's coming out at me. Here, this would give a negative curl. If I use the right-hand rule, that rotation would be going inward. And so while in two dimensions, it's just positive and negative curl, and then, there's some magnitude of this, how much it's actually rotating. In three dimensions, well, in general, there's going to be a direction to the amount of rotation given by the right-hand rule. And so the curl is actually a vector in three dimensions. And in two dimensions, it's also a vector, but turns out, since we only have these two directions it can go, out towards me or into the plane, like here, that's just positive and negative. And so in two dimensions, it's okay to think of this as a scalar, but in three dimensions, we really need a direction to the rotation. So this curl of a three-dimensional vector field will be a vector field itself. And I mentioned before, we used this notation of the del operator, del dot F gave the divergence. That was a scalar, because the dot product gives a scalar. Here, we can use the cross product of the del operator and my vector field F to give us the curl. Del cross F. We can compute this cross product in the usual way, using the determinant of a matrix, I, J, K. The del operator looks like partial with respect to X, partial with respect to Y, partial with respect to Z. And then down here I have my my vector field F, G, and H. Let me write that in line with it so it actually looks like a matrix. And so we can do the thing that we do to compute cross products. I'll cover up the first column and record the product of these two minus the product of these two, and that'll be in the I direction. Only again, I'm not really taking a product. I'm applying the operator partial Y, partial with respect to Y to H, and then applying partial with respect to Z to G. So this gives partial H, partial Y, minus partial G, partial Z in the I direction. Moving on to the J direction. J, remember J gets an extra negative, and so instead of going partial with respect to X of H minus partial with respect to Z of F, I'll go the other way with it. Partial with respect to Z of F, so partial F, partial Z, minus partial H, partial X in the J direction. and I don't want to get cropped out here, I'll scoot it over. And the k direction we'll have with respect to x and g, and partial with respect to y of f. So partial g, partial x, minus partial f, partial y in the k direction. Now check this out. Here was partial g, partial x. This was the two-dimensional curl, and as I mentioned, this either came in, out of the plane, positive, or into the plane. Now, out of the plane, into the plane, that's really my k vector, right? And so we're seeing that same thing here. So this really does generalize the notion of curl to 3 dimensions, and in particular, this is a vector. This is a vector, and so we should treat it as such. So this term, this measures rotation about the z-axis. Let's say that. Measures rotation about the z-axis. So that's in 2 dimensions. That was the only kind of rotation we could have, and that was given by these 2 situations. This one, the second one, this is in the j direction. This, in general, this measures rotation about the y-axis. And finally, this guy measures rotation about the z-axis. So this is in general the formula for the curl. Looks like this. You can use this, or you can always come back to, remember when I always did these practice problems when I was in Calc 3 and vector calculus, I always came back to this determinant of the matrix to compute my curls, but you could memorize this formula if you want. And remember that if in 2 dimensions, if the curl was 0 everywhere, we called it irrotational, and this had consequences for line integrals. So same thing here, that definition extends to 3 dimensions. If gradient cross f, or rather if del cross f is 0, we say f is irrotational. That is, it's not rotating in any of these 3 directions. Each one gives 0. This is the 0 vector, by the way. And we say that f is irrotational. And this will have consequences when we try and extend Green's theorem. Okay, that's it for this video. In the next ones, we'll take a look at some examples of curls of vector fields. See you there.